Welcome. Thank you for attending the session. First one kicking it off, feel honored. My name is Mark McBride, Senior Software Engineer at Capital Games, EA. I'm here with Bill Weiner, the Senior Vice President of Operations at 47Lining. And today we're going to share with you how we gather meaningful player insights using Redshift in AWS. So just to break down what you can expect from this session today, I'm going to start off and talk about how we came to our architecture, what it's composed of. And then we're going to jump into the challenges, the meat of the conversation. And Bill's going to jump into all the effective patterns that we've learned for ingest, deduplication, aggregation, really all the main components of having a data ingest system, balancing performance, rapid ingest time, and just best practices for schema optimization and performant data summaries. And importantly, how we built a Redshift solution to ingest 1 billion records per day. Pretty exciting stuff. Long time ago in galaxy far, far away, not that far away, but in Sacramento, California at our studio, Capital Games, EA, we were given the opportunity to build a Star Wars title mobile, so we were all huge fans, and we wanted to do something that we'd want to play. It was a very exciting experience. So not only did we want to create a great game, we wanted all of our systems to support that. So we looked at our data analytics system at the time and said, are we going to be able to provide the support for our players to really create a great game? So let me give you an idea of what life was before Redshift about 2 years ago. It was really just built on external solution that really had a one-size-fits-all for processing games. So we had all the standard key performance indicators like monetization, retention, and you could compare all the games, console, mobile, across the board. But what we lacked was really in-depth understanding of our players' abilities to do things like guilds and raids, things that were unique to the games that we were building. And probably one of the other things that was really a downfall is it was client-driven. Typically, we ship clients once every 12 weeks or so to the market because of all the certification internal and also within Apple and Google. So everything was client-driven, and that's how long it would take to get in a new hook to the game client. So that just wasn't sufficient. Most of the time, we would never put the hooks in because by the time that question was immediate, it wasn't immediate anymore. So here's the vision, really what we were looking at to build to support Star Wars, Galaxy of Heroes. So we wanted to discover how players were really playing our game to drive better feature development with healthier operations. We wanted rapid iteration. Like I mentioned, we wanted to be able to, if we had a question, put a hook into the system within a day and be able to answer those questions. This needed to be decoupled from the game server. We wanted to ensure that no matter what happened with Redshift or the reporting, our players were not impacted. It had to have frictionless access to data. We wanted to make sure all our data analysts were able to just jump in without any friction, and that it was easily queryable using something simple like SQL that everyone's familiar with. And then wall displays. We wanted the whole team to know exactly where we were at financially, the player features. When a new client feature goes out, did that raise the tides, or did we need to do more work on that? So now that we've gone over the vision, let's talk about the architecture and what was built. So the first part of the architecture is really moving the data from the game client all the way to the S3 buckets. We're going to divide it into two parts, and the next is going to get it from S3 to Redshift. So the major components of that are the game clients, the game servers, Kinesis to push the events through, our S3 workers to pull the events and push those into the S3 bucket. So let's dig into each one of those components into more detail. So the game client, it's a mobile client, iOS and Android. It produces client-specific events. So when a player goes into the game and say they go from the main screen into the guild screen, we're going to have a telemetry event for that. But we're not going to send it every single time that happens. It'd be very verbose and chatty. So we end up backing up all of those events. We also persist those events until the server acknowledges that they got that batch of data. The events are information is very important to us, so we don't want to lose any. So for an example, if the client crashes, events will be sent on the next session, which Bill's going to dive into what kind of problems that can cause because the data comes across as anonymous. So keep that in mind. Next step is our game server. It's just a bunch of EC2 instances that we auto-scale behind an Elastic Load Balancer. We're a Java shop deployed to Tomcat. Try to keep it as simple as possible. This is where we produce most of our events. Typically, we do server deployments once a week, but if we have a hot question, we just did a release this last Thursday and someone has questions about ships and how they're doing, how they're affecting our economy, we can jump in within an hour or two and have that in production and start to answer those questions. So those events are all sent asynchronously to Kinesis. We're using ActiveMQ as our broker. It's just an embedded broker that just runs a bunch of threads that's doing all of that work. That's also persisting everything to disk until Kinesis actually acknowledges that it got that information. Like I said, the data is very important to us, so we'll retry with exponential backoffs if Kinesis is down, which I'd highly recommend, or you just can't reach the host, you're having network issues. So after the retries fail, we'll go to the dead letter queue, and every hour or so we'll go through and make sure the dead letter queue is flushed again. So now we got the information on Kinesis. We've got a stream that has 10 shards. It's partitioned by an event unique identifier. Really simple. It's 24-hour retention. When we first built the system, that was the only choice that you had for Kinesis. Now I think you can go up to 7 days, but 24 hours works quite well for us. This provides fault tolerance to the game server. Like I mentioned in the vision, we needed to make sure that when we do run, if we do run into Redshift problems and it's Thanksgiving and everyone's at home playing, that they don't have to worry about that end of it. We can work on that problem separately. The game server also batches all the information into one Kinesis record on every client request, and these records are compressed when we send them across. And then finally, we've got our S3 Kinesis worker chewing on this stream of information that's coming through. We deploy it to Elastic Beanstalk. I believe there's 10, one worker for every shard. The first step it has is it decompresses the record. The step is transforming the hierarchical JSON structure into a flat structure that easily maps over to a Redshift row. And then we'll do things like patching missing data. I mentioned earlier we have some anonymous data. We've found certain tricks that we can plug player IDs into where non-standard attributes, and so we'll patch the data up. We'll also transform some of the data from like a 0 and 1 to a true or false. In addition, we filter out unrepairable data. Sometimes we'll get a client timestamp that shows from like 2100. That hasn't happened yet. So we'll go through and put that into a separate S3 bucket, and then we'll also have operational metrics using Datadog so we can keep track of how many times that's happening, and if we see a high rate, we can investigate it. And then we write to S3, flush to S3 when the thresholds are met. So we're looking at number of records, size of the buffer, or just the amount of time. So typically we flush at every 10,000 records, and that ends up being about 7.3 megs of data. And then finally, we're talking about S3. We organize our files by hour, starting with the year first. And then finally, the file name uses the Kinesis sequence start and end date to uniquely identify it. This is also compressed, and we think of this data as a long-term truth. We never go back in and try to change the data of what's happened in the past. Anything dealing with the next step is massaging it to what we need for our analysts. And just to point out, it's very cheap. It's such a minor part of our budget. It's pretty amazing how much data S3 can hold and how cheap it is. So now that we have all the information to S3, we need to be able to query it in a really easy way, as I mentioned before in our vision. So now let's talk about getting from S3 to Redshift. This is really the high overview graph. We use a lot of data pipeline jobs to do a lot of the orchestration. We're using Beanstalk for jobs for Deduper and analyzing. And then we also have data pipelines for vacuuming and doing some ETL. So we're going to jump into each one of those components to understand exactly what each one's responsible for. So the ingest data pipeline, this is the very first step of going from the S3 files to get them into a table. Every hour, we have a data pipeline job that goes through and just pulls the data from S3 using that hourly format and does a full copy of those into Kinesis, So that's really very fast. The copies of Redshift command slams it in there. It's really simple. Make sure you monitor for failures in here. There's been times where we've not been able to get a connection to Redshift, and it's not until sometime later that we find out that we're missing an hour's worth of data, which is pretty easy to do when you have 1 billion records for that day. And then something else just to mention on the side here is to consider manifest-driven ingest. We went with the hourly one for simplicity, but that really just means we can only ingest data at the fastest every hour. Doing more of a manifest-driven ingest, we could go even faster. So we're looking at doing that. And to give you an overview, I've talked about some of the tables. I just wanted to show a diagram of how the data is moving through. So we'll mention these tables a couple times. The very first table is our ingest table. Like I mentioned, that's where S3's copying all the data into. The next step is going through and deduping itself into the dedupe table. And in a second, I'll mention why we need to deduplicate, but that's a very important step there. And then finally, we put it into our main fact table, our events table. It's a rather large table that I'll also share the structure of that. And then finally, we have our ETL that pushes the data into our aggregates. All right, so the deduper, so why deduplicate? The easiest way to explain is that Redshift doesn't provide constraints. You can actually create the tables and specify them, and they'll be used by the query optimizer, but they don't enforce it. So you have to enforce it yourself by providing this deduplication. And then the reason why we'd have duplicate events is in our systems, with them being distributed, many times we're going to go through and retry an action if we're in doubt if another system gets it. So the server, and it's unsure, it doesn't get an acknowledgement from it, it's going to retry. So many times we'll get duplicates from that. Not to mention, like I mentioned a second ago, data pipeline jobs can fail. So you want to be able to rerun these ingests without concern with having duplicate data or bad data. So our implementation is pretty simple. You could go through and just say the whole column is what you uniquely identify that row, but it wouldn't be very performant when we go through and do the deduplication. So you really want to pick 4 or 5 columns depending on what your data looks like that uniquely identifies it for a row. So our implementation, it's a Beanstalk web app. It's just an individual one. It pulls this table, the events dedupes, and as soon as it finds data, it'll start processing it. You can see here the columns that we have on it. We've got the raw event timestamp, the player identifier, the session ID, and the session ID is generated every single time a player logs in, so it's unique to that player session. And then we have a step, which is a sequence number that's incremented for every single telemetry event that we fire off. And then we have the event type, which is basically for every type of event within the system, like a battle summary event or a battle summary event is a good example. And then I showed you the events table in the previous diagram. Here's the basic schema for it, highlighting the sort key and the distribution key. I'm not going to get into the details of why we chose those, but I'll just, because Bill's going to get into the details of that in a second here. But this distribution key is the player ID. The sort key is using a series of dates in the player ID. And then we also have the event type, as I mentioned before, like the battle summary event, your standard fields for every event, such as country, device, network, and platform. And then the event values. For every event type, you can specify that event can choose what kind of data they want to have in there. So for battle summary event value 1 could be the number of hits within a battle for Star Wars. And now we're on to the maintenance of that, really making sure it stays performant. So we vacuum, and the reason why you'd want to vacuum is that you want to reclaim any unused space. That could happen from updates, from deletes, and also from inserts. And really, we only insert, we never delete. So this is very important for the next step for analyze, so that you can have performant statistics for the query optimizer. We ended up going through and vacuuming once a day, which balances the time to vacuum with the quality of the queries. The next step we have is analyze, which is also a very important step. And this is really needed for the same sort of reason. Anytime someone's adding or modifying or moving a lot of rows around, having the unsorted area that Bill's going to get into much more detail in a second. So this occurs every time the table is vacuumed. And we also analyze every successful deduper process. It's very resource intensive, so similar to the vacuuming, you have to make sure you balance the time to do that and also your performance of queries. We get to our ETLs. The example I'm going to give here is a user daily. That's something very important to track within a game system, how long a player's stayed in the game. So this is a data pipeline job that triggers many different ETLs. Many of them have sequence of dependencies. For the user retention one, it depends on our user job that keeps an aggregate of all of our user data. Its job basically goes through and upserts table data into the table looking back a week in case we're missing any of the data that didn't come in due to maybe a game server being down for a day or so. An individual one, not the whole game, to be clear. And so basically, you can also see the sort key slightly different here, and it's really based on what your query workload looks like. So for this one, we've got our player ID, platform, country, and stat date. And then we also have other data that rides along, such as days in the game and revenue. So this was all really, really exciting. On the left side of this graph, you can see where we soft launch, typically games soft launch in different countries that looks similar to your larger, like North America. So you can see if all your KPIs, your key performance indicators are meeting what you're expecting. So everything went well. Worldwide launch was November 24th, a little more than a year ago. We just celebrated our first anniversary, which was exciting. But that was a fun week. It was over Thanksgiving, and to watch a system like Azure having Turkey scale up to 1 billion events, and it was just screaming. Everyone was happy with the analysis. And then what was even cooler about this is typically with games, mobile or console, you'll have a launch, and then you have this long tail. People go on to another game. But with the help of the Star Wars brand and people being excited about The Force Awakens, you can see here number of events went up, which you can see almost every other KPI for us went up also. So a lot of high-fiving at the office, and we're all very, very excited. We loved playing the games ourselves. So in every respect, we were succeeding. But there were some challenges, and at that time we contacted Amazon, and they put us in contact with 47Lining and Bill Weiner. And he came in and helped us out with some of those challenges, and we're in a much better place today. So I'll hand it over to Bill now.
Thank you, Mark.
Welcome.
So as you saw on the previous slide, there was a tremendous step function in events coming into the solution. And if people have made this type of solution before, you'll know how that probably went behind the scenes. As Mark pointed out, the solution didn't have a tight coupling to the gameplay, but there was definitely some challenges that occurred. I'm going to go over 5 challenges that we experienced during that post-launch window of time. I hope to show you the solutions we use for those problems, as well as show how these could be relevant or helpful to you. Let me start by reviewing Redshift architecture, just to get a baseline here. So the leader node, as most in the room will know, is the SQL endpoint for Redshift into the cluster. For this conversation, though, it's probably most important to understand that the leader node holds the metadata for the tables, as well as performs query planning. So it plays an important role when dealing with large tables like this. It is a clustered approach. Therefore, data locality and network transmissions are critical performance attributes that need to be understood and optimized. Ingestion from S3. As Mark said, S3 was definitely the route EA went, and that's usually the best route to go of all the options for ingestion into Redshift when you have this size of data. It's very, very large. There are 2 node families in Redshift, the DS2, which is storage optimized, and the DC1, which is compute optimized. There was an early choice, given their understanding of how much data was going to be coming into the Redshift, to go with the DS2. But as it came online, they quickly realized just how much compute load there is to ingest that many events and to aggregate the results of that many events on an ongoing basis, and ended up very quickly at the DC1 family. In fact, they used a DC1 8XL, which has 32 slices per node, and that'll be an important statistic coming up here in just a moment. So as Mark showed in the graph, the number of events coming in took a step function, but other parts of the solution did not react quite as well. In the blue is the vacuum time. At this point in time, it was an hourly run after each ingestion. Yes, 650 minutes is nearly 11 hours. As most can understand, that didn't work very well. A temporary stopgap solution was done at this point to move it to a nightly process in order to be able to run this long in order to produce a vacuum table. That was, again, stopgap, simply because you can see from the slope of that blue line, it was going to quickly get over 1 day to vacuum this table. To the right of that, shortly thereafter, the deduplicator started running very, very long times. It was not successfully completing the analysis to deduplicating the incoming hourly stream. We also needed to address this issue quickly in order to keep the data flowing. And as you can see by the graphs, we got both of these nailed. I'll show you how in just a second. Let me start by helping you understand the goals of sorting, and it played a huge role into what these problems were all about. So sorting is a physical process that actually takes the data based on your sort keys, and it will put the data in rows in that order. It's very literal. The vacuum process, if they aren't initially in that order, will be what puts it into that sort order. One of the key attributes you're looking to achieve is reduce row scan, the RR scan, as you see up there, as well as what we like to call block rejection, which is a very similar term, and I'll get into that in just a second. This is the ability for Redshift to prune the number of table blocks that need to be read in order to perform any query. If you can optimize against this, you can achieve very high performance against very large tables. So the sort keys are critical for the vacuum process, as I was just explaining. They set the end state for a sorted or vacuum table. If that is very different than the pre-vacuum state of the table, a long time could occur, resulting in graphs like we just saw. So in choosing a sort key, it is really important to think about your common query predicates. These predicates are what's going to be used to do that block rejection, and the block rejection is going to compare to metadata, and the metadata extents are going to be changed by the sort keys. So lining all these factors up is really important. I'll go into this in much more detail in a moment. However, there's another important attribute that needs to be maintained, especially for what's called a time series data table, a table that has data added to it over time. And that is to make sure that new data, which is going to be inserted at the end of your tables, after vacuum, remains at the end of your tables and not spread out, causing a lot of reordering of a very large table. Further, Redshift supports two sort key types or methods. First is compound, fairly straightforward. You give it a list of columns to sort the data by. It will first sort by the first column, column 1. And then anytime column 1 is equivalent between two rows, it will use column 2. And if those are equivalent, it will use column 3. It's a very hierarchical in-order sorting methodology. The other method is the interleaved mode that gives a more blended or balanced approach to what data is going to be sorted elsewhere. And it can be extremely effective on very large tables. However, it is not really an appropriate choice for time series data that is changing rapidly. It's an appropriate choice for very static large data sets. So it is not one to be used in this solution. So looking at some of the documented best practices for time series data, it is important to understand about the primary or first listed sort key. That's the one we're going to focus in on at this point. It wants to be monotonically increasing with the data as it comes into the solution. And that's to keep the data at the end of the table post-vacuum. If you think about it, you are adding layers or strata to your fact table with each incremental addition or insert into your table. You want to preserve these strata as you go through the vacuum or sorting process. If this is not done, there'll be a massive reordering of the table that has to be performed. It's going to move a lot of data, and moving a lot of data will result in a lot of time. Pardon me. So Electronic Arts, as Mark was presenting, did try to set things up exactly per all these best practices. They chose a very appropriate time, as far as they understood, for the primary sort key. Vacuums, unfortunately, did grow very long, so what happened? So the data arrives on the ingest table and wants to be inserted towards the end of the main fact table. It actually will be inserted at the end. That's the only place Redshift can insert data. They had used a timestamp of the gameplay event for the primary sort key. So as people play, An event is created, goes through the solution, ends up at the end of the table, all should be good. However, they used a timestamp that was driven off of the client system's clock. And this client system clock, in some extremely rare cases, and I mean parts per million level, were very wrong. I'm not talking hours, I'm talking decades wrong. These massively out-of-place events were creating a situation that when vacuum came along, a few rows had to migrate from the bottom of the table up to the middle or the beginning. Redshift needed to open space for them and shift many, many millions, billions of rows. This took a long time. As you saw in that chart, it took 11 hours. Our best understanding for what was going on here is that game players, they just like to play games. And they thought they could get an edge by changing their system clocks. But unfortunately, it was causing us a significant problem with vacuum. So we needed to address these out-of-position events. How did we do this? We changed the primary sort key of the table. We changed it to one that was corresponding to the Kinesis worker timestamp. This was already coming through in the data stream. We already knew when it was coming through Kinesis. This clock was now under the solutions control. These games were eliminated. It is really important that when you're dealing with very large time series data, that the data stays at the end, because you got a massive load of data and you don't want to be moving it all. This also shows how important it is to exactly know what's in your data. Well, we're talking a minute number of events were causing a massive vacuuming problem. So the compound sort key was a fairly simple change to allow us to address the vacuum issue. The deduper was a very different problem. And to understand exactly what was going on, it's best to review sort of best practices around a compound sort key. So this is that order list, and as this is taken directly from the Amazon documentation, you can see it attempts to show that the benefits of secondary, non-primary sort keys, it actually says decrease when queries depend only on these columns. As you saw on Mark's slide, the deduplicator needed to look at things as event type and step, and some of these other columns had nothing to do with when the event came through the Kinesis worker. There's actually two events coming into the solution that were duplicates were very likely to have different Kinesis worker timestamps. So it was not appropriate to be looking at this. So we needed to look at non-primary sort keys. Primary sort key, fixed vacuum. Now we have a secondary problem. It is important also that these secondary sort keys are predicates for your queries that are very common. And so in this case, we were picking things like event type and step, things the deduplicator needed as these secondary sort keys. Our challenge at this point to get the deduplicator to work quicker was to change my insert of may in the last sentence of this slide to a won't. Compound sorting based on these secondary keys won't decrease performance. To understand how to do this, we need to look a little deeper into zone maps on Redshift. So zone maps are a zone or block on Redshift is a 1 megabyte chunk of data per column, per table, for everything on Redshift. So these 1 megabyte blocks of data all have metadata. This metadata keeps the min and max extent of the range of that column for that 1 megabyte. This information is known as the zone map for that block of data. So when you sort data, clearly the rows that get together within that one block are going to change, and the maximum extent of the data ranges for that block will be different depending on how you sort the data. So we want to think about how can we sort the data to change the metadata, the zone map, for each of these blocks on these columns that we're very worried about. So to think about this attribute of the zone map, what we have to do is let's step back to a query that would be running. And a query that you would run, the first thing that would happen is the predicate clauses, the wheres, would be compared against metadata for the blocks for those columns. This was done by the leader node before any of the massive amount of data is read off the disk for the full extent of the table. If it can determine that a block of data does not need to be read off of disk in order to perform the query, it will not read it. And this is why at 47Lining we have come to call this block rejection. And you want to try and maximize the amount of blocks you can reject on these large tables to minimize the amount of data that needs to be read into the cluster. It's also important that the data is analyzed. Analyze is the command that will update the zone maps. If your zone map data is invalid, it will not use that information to reject blocks. So keeping it regularly analyzed is critically important. So how did we get better block rejection using zone maps on these later sort keys for EA? I'm going to have to go to a very super simplified example because there's a lot of moving parts in this, but let me attempt to get the essence across. Here we go. So up here I have a table, and in this table it has 3 compound sort keys: sort key 1, sort key 2, sort key 3. And they're sorted in that order in this table. And literally, if you look through the data, you will see that almost all the work is being done by sort key 1. This is very similar to what was happening at Electronic Arts. That Kinesis worker timestamp was doing almost all the work. Later keys were not. So what's the upshot of this? In this super simplified example, I've defined a block to no longer be 1 megabyte of data, to be 4 rows. Fits nice on a slide that way. So you can see I've, on the left of the slide, indicated what a block looks like. If we were to look at sort key 1 for block 1, we can imagine in our heads what the zone map might look like for that section of the table. It would have a minimum extent of 1 and a maximum extent of 4. And going down, you would see for block 2, minimum extent of 5, maximum of 8. Very nice. They're non-overlapping. Should get good block rejection on that, but that's not the ones we're worried about. Worried about sort key 2. If we look at block 1 for sort key 2, we can see we have a minimum extent of 4, but a maximum of 11. I got a very wide set of metadata for my zone map on this next column. What happens is this leads to poor query efficiency when you are just querying against these other columns. You're not using sort key 1 as your predicate. We're using 2 and 3. So as an example, let's look at a predicate that would be sort key 2 greater than 9 and sort key 3 less than 4. Simply from a zone map or metadata point of view, I can look down here and I can see for sort key 2 in block 1, I have a value greater than 9 somewhere in the block. I got to read that block in from disk and find out if I need to use the rest of it. Down you go. The next block has a 15. The next block has a 10. On sort key 3, I got a 1, I got a 3, I got a 2, I got a 4. All these things are matching and creating a situation where I need to read these blocks in. More data has to come into the cluster. More work has to be done. As I mentioned, the main issue here is there's too much sorting power in that first sort key. I want to smooth it out a little bit. In order to address this problem, let's look at truncating the data for sort keys 1 and 2. So in this simplified example, I'm going to take a synthetic column. This is an additional column in your data, not a replacement of your original sort key. So synthetic sort key 1 is the decade of the information on sort key 1. Similarly, synthetic sort key 2 is the decade of the information for the original sort key 2. In this table, I've now sorted by synthetic sort key 1, followed by synthetic sort key 2, followed by the original sort key 3. What you can see here is all of a sudden I get nice clumping on those later original data points on sort key 2 and sort key 3. The things I want to write predicates for have started to clump together and give me better information, better rejection of what information is in those zones versus my first example. It's in this way that we tackled the problem of getting the deduplicator to be faster. We needed to truncate the information within the Kinesis worker timestamp so more events had equivalent values for that first sort key. However, doing this presents a new balance point that needs to be considered. So in the picture here, let's assume my 4 colored bands on the left is my ingest table, where I have brought in 4 hours worth of information, but I am truncating that timestamp to a 4-hour window. So these 4 hours worth of data will have the equivalent value for this truncated timestamp. What that's going to result in is when you vacuum, all those rows have to be interwoven. That creates a lot of data movement and a lot of work. Not as much as we saw in the original problem with those few out-of-place events, but significant work. But what this does is it means a lot of events are coming in with exactly the same first sort key value, giving more power to those later sort keys. So you're winning on the sort key power side, but vacuum is taking longer. And this is the trade-off that needs to be factored in here. You have an ingest rate, how often am I going to bring data in, which is going to determine how timely my information is from my people with their dashboards. I got the vacuum time, which has to do with how many rows do I have to keep sorting together when I do this, as well as the power I'm reserving for those later sort keys and predicates, the ones that are being set up to give me information that I need for my actual queries, not just keeping the overall table in a roughly sorted way such that the vacuum process doesn't go into the weeds. So this balance point is critical, and it's solution independent, because it's the other variable coming into this, of course, is the volume of events coming in at the input side to determine how many of those will fit in a 1 megabyte block. For this game, what was decided is to go with a 1-hour ingest with a truncation of 1 hour. That kept vacuum well behaved. Those things matched pretty well. As I mentioned earlier, we used the Kinesis worker timestamp, and we were truncating that. There were some rough edges. There's a little bit hour-to-hour overlap, but that was well within the ability for the solution to vacuum those out on a nightly process. And lastly, the sorting power came from this level of truncation, and the high volume of events coming in meant there was lots of block rejection on these later sort keys. These 2 sort key changes are what was used to address those 2 very large spikes you saw as the volume increased. So what happened next? So we get past the 2 large spikes. This is the same chart I showed earlier with an extended time scale out into time, about a month and a half. We can see the deduplicator, again in purple, slowly getting worse as things accumulated. There was something creeping in the system. It was no longer a loud issue, but a quiet one, but still needed to be addressed before this solution was deemed to be fully acceptable. These issues were affecting almost every query in the system, not just the deduplicator. So it was something that needed to be addressed in order to ensure that a whole bunch of work could get done. To understand the root cause behind this, we need to look at distribution. There were many causes for this. The biggest was a distribution issue that was subtle. Looking at distribution, you can see there's 2 main goals you're trying to achieve with distribution. The first is to co-locate your data within a slice or a node. And the reason for that is, of course, you want to aggregate data or join data. It's much faster to get those pieces of data together if they're on the same physical CPU. The other one is to distribute the data throughout the cluster in an even way, because the distribution of the data determines which CPU or slice within the cluster is actually allocated to do the work on that data. So that assignment of initial work is made by your distribution key. There are 3 modes of distribution in Redshift, shown here: distribution by key, which is to use one of your data columns and its value to determine which slice within the cluster the data belongs to. All, which is simply to put a copy of all your data for that table on each of the nodes and assign one of the slices to be the owner for performing the work on the data for that slice. And the last is even or round robin. It's one that just distributes the data evenly. when choosing these, you need to look at the relative strengths of each of these modes to understand which was the best choice. A distribution of all, as I said, is one that distributes the data on every node. It's very useful for dimensional tables, especially ones that don't share a common distribution key with your main fact table and prevent large amounts of data network traffic in order to create a join, for example. The downside, of course, is your data is replicated, so it's going to take up more space on disk. So it's only appropriate up to a certain size of table. Even is frequently used. It's also the default. It is very good for making sure your data gets evenly distributed, that each slice in your cluster has an equivalent amount of data to work upon. The downside with the even distribution, of course, is it's guaranteeing no locality of different rows. So if you aggregate on some field or you have to join, there's very high likelihood that data is across the network, and a lot of network traffic will be generated by that event. Key, of course, is the best to use, especially as was done with Electronic Arts. They were to set the key to be the player ID. A vast majority of the aggregations that were done were based on players. What is this player doing? What are they about? How often they get on? Those kinds of questions. So distributing by player made sure that all the player data for every player was on a slice, and that slice could do all the work to aggregate or join. The downside with key is it's up to you now to make sure your data is well distributed throughout the cluster. It was this last point that got in the way. I'm sorry, let's deal with one more slide. It was best practices. I talked about two important pieces: to distribute your workload uniformly among the nodes of the cluster. This was absolutely well done by the player ID selection. But you also want to reduce the data movement, which also should have been well done by the player ID. So something went wrong in these selections that was causing a problem. Mark alluded to this earlier, which is there was a fairly high percentage of information coming through where the events were marked as unauthenticated or anonymous. These were events that were created before a player had logged in, or a problem in the telemetry system that it wasn't filling in all the necessary information at this early date. What happened is roughly 3% of the events at this time frame had this unauthenticated value for their player ID. And since the key that was being used to distribute the information was based on that column, all that information piled up on one node. That gave us roughly a 20% overload on the storage of the node. Not great, probably not awful. So initially we didn't notice how out of skew this table was. As we saw the slowdown occur, a deeper analysis showed that if looked at by slice, by which CPU the data was assigned to, there was a 9x additional load on this one CPU. This one CPU was quite overloaded. It was taking the longest to return its results, and it was causing all sorts of queries, even if they weren't dependent upon the events table, to slow down. So it's really important to understand the full extent of your data. Know your data is one of the mantras I like to keep saying. And in this case, a small percentage of events that shared this unauthenticated value created a very large performance issue on the cluster. To address the problem, what we did was we split the data between two tables, an authenticated events table and an unauthenticated events table. The authenticated events remained on the player ID distribution key. This allowed for all those aggregations for all the known players to happen and for the data to be easily and efficiently aggregated. The unauthenticated events were partitioned off to a separate table with an even distribution. So now they were going to be evenly distributed around the cluster. What this meant is no longer we had a distribution problem, and most of the aggregation routines were not looking at the unauthenticated events to find out player statistics. They knew those were uninteresting events. We replaced the original events table name with a union all view of these two tables. That meant no query code needed to be changed. It all ran against the view instead of the original table, and it ran significantly faster. Again, it is critically important to know your data. So this was the most significant, but not the only reason for that long tail slowdown. The deduplicator was also being affected by the fact that the deduplication of events was looking across the entirety of the ever-growing events table in order to find the duplicate event. Even with fantastic block rejection on all those secondary sort keys I just talked about, that data set was growing and growing and growing day after day. What needed to happen is we needed to shrink the amount of data down to a limited time range, and this was possible because of this truncated Kinesis worker time. We knew, based on that field, when they came through Kinesis. So based on some overly conservative analysis, we were able to determine 3 weeks, 4 weeks. You don't need to look back farther than that to find the duplicate, because they are not going to be that far through the system. I mean, to 7 sigma kind of problems. We were able to limit it down by this new primary sort key to only look back a few weeks, and this allowed a very uniform or static amount of data to come through the deduplication query. This made the deduplicator table size invariant. Before it was searching the whole table, the amount of data it needed to walk through was ever increasing. Now it is limited, only grows if the number of events per hour grows into the solution. The other side of this was aggregation. The aggregation times were also growing, primarily because many of these were also searching through the entire events table for results. This made an aggregation process that was also slowing with time. Even though all these player IDs were co-located on the same slice and running fast, they were dealing with more and more data as the solution went forward. These also needed to be found a data table size invariant pattern in order to be stabilized relative to the size of the events table. To do this, we went to an incremental aggregation approach. So basically, just look at the last few days of information for all your players, find their statistics of what they have done over the last few days. That's fairly simple. That's adding a where clause to your query that was already existed for this aggregation. But then the hard part begins. How do you take that limited time range piece of information and merge it with your historical aggregate data? It doesn't always just magically line up. Sometimes it adds, replaces some other process. These can be very complicated sets of querying analyses and optimizations. However, this is critically important if you do want a solution that's not going to slow down over time. You need to think about if you're dealing with time series data, it's likely to keep growing and growing and growing as more data comes into your solution. If you wanted to keep performing at a predictable rate, you probably want to think about how do I set up analyses that are more table size performant invariant. There's an additional benefit that comes along with this process. Now these aggregations no longer look at older events. Not that these aggregate tables don't have information that go back to the beginning of time. They do. You have all the information for all players in the aggregate tables. But for the events table, you're not scanning those events very often. This allows for the ability to do data retirement. One of the issues that often comes up when you start putting data into Redshift, into your warehouse, is it grows. And it keeps growing as more data is available. Setting yourself up for ability to retire data is critically important. So with that, I'd like to turn it back over to Mark, but just make that point one more time, that it's critically important to think about how you can make your data solutions keep performing with time.
So thank you, Bill. That was awesome. It's been great working with Bill. We've learned a lot about Redshift, and the vision's been realized. We have many events going into the system. It's very performant, and we're really looking past the vision now. What's the next step? What do we want to do? And let's see. And then we're also looking at adaptive AI. If you've ever played our game, if Wookiee's the last person standing and he taunts, which is basically just saying, hey, fight me, that's probably about the worst move he can make. We can actually pour in all of this data and find what would have been a better action to do there with our rules and our AI not being as good as learning from the data of like what is the better move to do to actually win the battle. So really we're changing the definition of success. It's not just about querying the data that we're looking for, it's also finding information that's really hard when you have this much data. So let's go over the next steps of what we're looking at. So Bill mentioned that we've got this huge fact table, billion events a day. It gets rather large, so data retention became a really hot topic for us, and mostly because of cost. Expanding our cluster was something that we did. It was an easy way to continue to scale, but it just wasn't cost effective. So Bill's actually helped us with this also. It's in place now where we only keep 6 months worth of data. And then if we want to do lifetime analysis, we'll fire up a cluster and maintain that one and do analysis on there. So we only need that cluster when we're doing the lifetime analysis. So that's really helpful and cost effective. I've already mentioned machine learning. There's a whole bunch of solutions out there, but it's a really hot topic for us right now that we're looking to use. Also, at the time when we built this, Firehose didn't exist. I'm sure many of you guys are familiar with Firehose, and we're looking at it. It's doing much of the work and heavy lifting that we're doing already. So we're looking at either being influenced by what it's doing or even replacing some of the components that we have. And then finally, Kinesis Analytics. We'd love to have a wall display that shows a map, a global map with every single time there's a transaction coming into the system. Just really neat stuff like that to get real-time information. So that concludes the talk today. I really hope it helped to share our architecture and also some of the mistakes we made. They're very minor, but they can be very loud once you have so much data. So I hope Bill's and my presentation helped you get to there, and thank you for your time.